And start the recording. So welcome everyone to the Air-Sea Fluxes from Space webinar series. Today we have Baylor Fox-Kemper from Brown University, who's going to talk about are fluxes indicative of boundary layer forcing or oceanic climate change? So I'll let you take it away, Baylor.
Great, thanks, Sarah. Nice to see lots of folks, familiar folks, and some other folks that I'm happy to maybe get to know a little bit through this conversation. Share, the right way, share. Okay. So, Air-Sea fluxes are really interesting for lots of reasons. I wanted to contrast a little bit thinking about Air-Sea fluxes from kind of a climate change perspective and what the requirements are, observational requirements are to use them in that perspective versus what Air-Sea fluxes might be when you're thinking of a boundary layer forcing or process modeling approach. And I was going to give a few examples of those pieces and highlight some of the challenges from the perspective of a modeler, from the perspective of both climate modeling and process modeling. And so I'm going to also talk a little bit about the IPCC modeling effort and how the IPCC fluxes piece came together. So I'll touch a little bit on that. And in that regard, I saw Lisan has joined already. I will thank Lisan for being very helpfully providing all kinds of really interesting flux data under very tight deadlines, as the IPCC always goes. That was very helpful at that moment. So some of the slides definitely require some credit to Lisan, who was a coordinating author. A contributing author for our IPCC chapter. And that's why. Okay, so maybe a useful starting point is just to think about some of the numbers that we might consider. Starting from the solar constant, right? That's how bright the sun is out in space. Only a quarter of that ends on average on the Earth because you have night and day to deal with, and the cosine factor. And there's some other things of kind of similar magnitudes that you might think about, like the reflected solar that's going back at the top of atmosphere, or the outgoing long wave at the top of atmosphere. So the imbalance among these is really that's the net change in energy of the Earth system, which is a small number. These actually cancel very, very close to canceling. When you get down to the surface, you have both upward long wave from the ocean up and then downward long wave from the atmosphere down to the ocean. And those are two very big numbers. That a much smaller number is their net effect. And then the solar incoming is also a pretty big number, and it switches on and off all the time from day to night. Another factor that you might put in this next category down is the upward latent heat. Sensible heating, depending on where you are, could also be in here, but sensible is harder to make a clean number for. And now we're in the kind of 10 watts per meter, 10 to 100 watts per meter territory rather than hundreds or thousands of watts per meter squared. Now is when it's kind of interesting to start thinking about how models do or do not represent these fluxes, how accurate models are. So a long time ago, Susan Bates led a paper that I was part of where we tried to estimate the CCSM4, so essentially CESM1, how accurate were its fluxes compared to the core flux data set, which is not really, so core forcing, this is Large and Jaeger's work, is not it's not exactly a flux measurement, it's a corrected flux measurement for the purposes of forcing ocean models. And so it makes sure that the large scale budgets kind of work out. So it's interesting to think about how much difference you get between that corrected forcing product versus the fluxes that occur naturally in a coupled Earth system model like CCSM. And in this particular model variant, the incoming solar differed between those two products by about 10 watts per meter squared on average. The latent heat by about -6 watts per meter squared. And the net air-sea flux was about 1.5 watts per meter squared. So now we're getting down to single-digit territory, which is good. But the spatial patterns the spatial differences between these, so the root mean square of the spatial variation from point to point, are still in the kind of 20 watts per meter squared region of the solar or latent or the net air sea. So that's about how well we can model things. We can get a pretty low number for the overall net. Individual factors might be order 10 watts per squared meter difference. Spatial patterns might be 20 watts per meter squared difference. And then those stack up to these overall budget factors that are, 5 to 100 times bigger than that. So that's a setting of how maybe a climate modeler might think about this. From an observational perspective, we know what the observed warming of the oceans were, at least to within observational uncertainty, and that's 0.74 with a likely range of 0.6 to 0.86 watts per meter squared. So not over 90% of the anomalous energy that I said was the imbalance here ends up in the oceans. It's comparable to, in scale, to at least what this model's imbalance was at the surface versus an observational data set that was meant to match this one quite closely. So doing climate change by fluxes is very hard. You are taking very big numbers, differencing them, ending up with smaller numbers, differencing those and averaging them over the year and ending up with smaller numbers still. And the signal that we're after is quite small on the bottom of that list. Now, you could say that an interesting alternative, which maybe we'll come to this in the discussion, is to say that actually it's really the ocean uptake that drives this whole thing. So Steve Griffiths has, in particular, has shown, and other folks at GFDL have shown that a nice way to think of this number is that it's actually really how much heat do you put down into the deep ocean. And then if there's excess heat left in the surface, then the flux is just eliminated away. It goes back to space. It does whatever it's going to do with balancing out the fluxes. So to say that the fluxes drive the system is maybe, oops, I got all the way to the end. To say that the fluxes driving the system is only one perspective. Within a coupled system, kind of everybody's driving everybody. So that's important to keep in mind. Okay. So here's the outline of, some of the ideas to keep in mind. But now I wanted to jump into a few topics that are kind of related to this. I wanted to first talk a little bit about how the CMIP fluxes compare, the coupled model intercomparison project, or the IPCC model, the models that are looked at primarily in the IPCC, how their fluxes compare to observations. Then I want to talk about a couple different ways you might use the oceans themselves to keep track of what the fluxes have been. That involves waves, it involves temperature, it involves mixed layer depth. And then I want to talk a little bit about mixed layer biases. And then I'll close by just some general ideas about how you can kind of still operate in this space, even with these relatively large uncertainties, by bringing observed fluxes into the modeling game in a meaningful way. Okay, so this is the flux figure from the IPCC Ocean chapter. So there's freshwater fluxes along the top, heat fluxes along the middle, wind stress along the bottom, so momentum fluxes along the bottom. The observation ones are just shown here, and this is the average observed fluxes over that 20-year period. Over those 20 years, you can take, here's the map of the observed trends, so they are changing a little in some places. It's important to notice that the scales are different here. So this is only a tenth of this. So the trend per decade is only a tenth of this guy in rough magnitudes. And then this is what the rate of change is looking out from kind of present day to the end of the century is what models project. And the thing I really wanted to highlight here, so you can look at these and maybe recognize patterns that you see, like the ITCZ or El Nino region, whatever, the Gulf Stream, Curcio, the normal things, ACC, that you see in as big signatures in heat fluxes or in momentum fluxes or precipitation fluxes. But the stippling here is really important. So the stippling on the observed trends is asking whether the trend is significant beyond the background variability. Most of the world in all of these is stippled out, which means that there isn't a detectable trend over this time period. So one way to take that from a satellite observation perspective, even if we flew a new satellite, we would still have a signal to noise problem in trying to directly observe trends in fluxes. Now, we didn't actually create how much of the mean signal is significant versus background variability, but if there's an imbalance in the means, that's still climate change. You don't actually need a trend in the fluxes to have climate change. You could just have an imbalance in the means, and that would drive a climate change. And there are details about how this is calculated, but essentially you can think about that those other regions that have the kind of smaller numbers as not really being detectable in their change. And they have not, the climate change signal in those fluxes has not emerged, is what we would say from a kind of climate science language perspective. Over here, on the right-hand side, now this is the models, and the hashing here is showing where the models don't agree on the sign. So how do we read that? Well, that is also the regions where the signal is small, so that the changes in the fluxes in those regions doesn't seem to be projected to be very big by the models. But there are consistent regions where the not hashing is missing, which means that all the models agree in the sign, at least, or over 80% of the models agree in the sign. So consistently, the equatorial Pacific is going to have more freshwater flux toward the end of the century, which is consistent with the acceleration of the hydrological cycle through the Clausius-Clapeyron uptake of more moisture by a warmer atmosphere. And you can stare at the other signatures and see, and there's interestingly different patterns between the heat fluxes and the freshwater fluxes. Even which regions are significant is different. And then the wind stresses, of course, are a totally different signature. But because the wind stress or the wind speed goes into the heat flux and evaporation piece, there's also some connections between these. So what's not shown here is any of those numbers giving the balances that I just talked about. And that's because it's extremely difficult in the face of all this uncertainty and disagreement to get those net balances down from the flux observations themselves. So instead, the approach that we talked about, the traditional approach from the assessment of climate change perspective, is you use the oceans themselves to keep track. And maybe the simplest one to think of is that you use the significant wave height to indicate the wind, because the waves are keeping track of how much wind they have experienced. And so they're a great integrator over all of the variability at the surface. And so this is up here is just showing observed significant wave height. This is from a nice paper by Mark Hamer. Here's the observed significant wave height, and it's in meters. And so then you can say, well, how about if you try and make like a wave watch style, a wave model estimate of this? Well, that's that model observational mismatch is about an order of magnitude smaller. So there's plenty of signal to compare to the observations, and those observations might be driven with different wind products, for example. And then you could get a handle on which ones are doing a good job in reproducing this. The multi-model, so this is kind of the absolute error. So that's mismatch. And then there's a bias. So the mean difference, and that's also a relatively small number of both signs in this case, of about a tenth of what this is. And then the different observational products, whether you're using wave buoys or satellites or whatever, that inconsistency is also pretty small in comparison to the overall signal. So unlike the wind stress over here, where everything is stippled out, pretty much everywhere in the world, we have a small signal to noise problem and also a small model versus observations thing to check out when we're talking about waves. So the waves are keeping track of the winds for us, at least some aspects. And so that makes it a nice detector of what's going on. And significant waves are the big waves. So this is sort of the long-term integration, but of course, scatterometers are looking at the little waves at the same time. So all of that is kind of together in this piece. You also can use the temperatures and salinity changes to keep track of what's going on with the fluxes as well, because the ocean is paying attention to what the temperatures and salinities are doing. So if you think of sea surface temperature, that's one thing to think about. And this is sort of a similar kind of figure. We zoom in and just look at the sea surface temperature. Here's the climatology. Here's the bias map. Here's the high-res model bias map. Then here's some observational trends, modeled trends over kind of the present day period. And then looking out to the future, it's just model projections. In this story, the model projections are actually all pretty aligned with one another between the high-res models and the low-res models. Also, only a small region is stippled out, this warming hole in the North Atlantic where AMOC changes have a big impact. So the projections are all kind of consistent with one another. The trends are fairly consistent, at least over large parts of the Earth. The stippling is much less of a feature now in the observed rates because we have a lot more observations of sea surface temperature than we do with fluxes. This is a longer averaging window, so there's more chance for a trend to emerge. And so this integration by the system, it really helps in pushing down the noise versus the signal. The bias pattern is interesting too. It's hashed everywhere, but you actually, that when you're measuring the bias, if the models don't agree on the sign of the bias, that's kind of a good thing. That means that your observations are sitting inside the envelope of model spread. So your observations are within what the models predict when you're thinking of stippling out a bias. So without going into too much, oh, what just happened? You can do this to play the same game with ocean heat content. And then, of course, it's trickier because you have to think about what depth you're looking at. I'm not going to go into too much detail, except to, again, point out that in the bias maps, there's lots of stippling, which suggests that the models are not, they don't agree about whether they're different from the observations anyway, is the way to think about that, either in the surface or the upper ocean depth. And they tend to agree pretty well for what the future patterns look like. And then on the side, it's kind of the same story. Again, focusing on the CMIP bias question. The only thing that really stands out, at least to my eye, is that North Atlantic deep water is definitely wrong in the models versus the observations. It's consistently wrong by a couple up to, a couple degrees on this multi-model average. So there's something funny going on there, which probably does deserve attention. And that really sets the global, this is a zonal mean, so this is a zonal mean over the globe, Pacific, Atlantic, and Indian. So the global mean also is kind of reflecting that Atlantic bias. And a little bit, there's this Indian bias, which also jumps in there as well. Okay. So one thing you can do when you're thinking from the climate perspective is not pay attention to the fluxes themselves, which isn't the story that the observing fluxes from space group wants to hear, because that's not the goal. If you want to observe fluxes from space, you want to say, well, they could be useful to observe them directly, even if these imbalances are large. So there is a different pathway to get to, which is the alternative of looking at that, which is going back toward process level understanding and looking at places where those fluxes are not so cleanly in balance. In the climate problem, they are in balance, like I said, because the ocean kind of adjusts to what it needs to do and then changes its fluxes correspondingly. If you don't, if you go from region to region, there's not enough time for that to get set up. So one indicator of that, that's maybe the most obvious one, is to think about observed mixed layer depth. So here's the mixed layer depth in wintertime and summertime, as observed on the left. Different observational products are kind of similar here. There's some smoothing here to remove missing data and stuff, but this is basically an Argo. These are essentially Argo products over a relatively Argo-like period. Again, the mixed layer depth bias, so the CMIP models is hashed everywhere. And so you say, oh, great, the mixed layer is most of the time within the models. I'm going to come back to that in a second and say why that's not such great news in the particular case of mixed layer depth. Except in wintertime, the mixed layer is too deep in a few places, and in summertime, the mixed layer is too shallow in a few places, consistently. So that means we're doing something wrong in either the specification of the fluxes, so the atmosphere could be wrong that's doing this, where it's too windy, it's cooling too much, or it is the mixing that comes on the ocean side is wrong, either through parameterizations or through model resolution. All of those pieces play into this. And when you look out toward the future under low future emissions scenarios, so the low end of things, basically the mixed layer doesn't change in most parts of the world, except for a little bit around AMOC and a little bit around Antarctica, where there's some deep water formation changes in wintertime. And in summertime, there's a little bit of a signal in just a few places. If you go to the strong limit, to very strong emissions, then basically the mixed layer gets shallower over most of the world consistently over all of the models. That's interesting because some recent observational campaigns have said that the mixed layer isn't obviously shallowing, even though the stratification is going up. But I think all of those are safely in this territory where we just don't where there's still a lot of changes going on. And we haven't really, the signal hasn't emerged yet. We have to really go farther into the future or under stronger emission scenarios before we get a change that emerges from the background levels. Okay, so mixed layer depth. So we have a hint that mixed layer depth is something we can think about. And mixed layer depth, of course, if their biases are big and they're sign definite, then we have a target of how we can improve models. So mixed layer depth biases are big, and they're in places where the fluxes don't actually cancel out very evenly. They're in places where there are large air-sea exchanges of net heat going one way or the other. The tropics and deep water formation sites. So there are big exchanges going there, and western boundary currents as well. So this is a study that a student of mine and I worked on, which I need to revise and resubmit. But anyway, I will continue showing it because I think it's really interesting in a lot of ways. But Galen examined the mixed layer depth from observations and from CMIP models in 3 different regions that are kind of where these big changes are. A Southern Ocean band, this white bar, a Northern Ocean band, which is primarily this guy in the North Atlantic, and then a tropical band. And we were surprised to find out that the dynamics of those 3 mixed layer depths is really different in the water masses that it creates, which is more than the story I want to talk about today. But on this side, we're just showing the scatter of the CMIP models. And it doesn't matter right now what these vertical axes are, but to say that the observations, we stipple here, the observations are within the mixed layer depth spread among the models. I said that was kind of a good thing, but now look at the numbers. It's pretty easy to be within the spread of the Northern Ocean mixed layer depth if it goes from almost 0 to 400 or 350 meters. The whole observed range is only this little narrow bar. The same is true in the tropics. The CMET models are going from, whatever that is, 18 up to 70 meters. And the observed range is between like 42 and 45. So we're missing the spread by whatever that is, 5, 6 sigma in terms of what the mixed layer depth is. And this is not sensitive to the mixed layer depth definition. This is that we're really quite far off in the modeling of mixed layers. And the same is true in the Southern Ocean as well. And here the consequences are particularly worrying because this is where a lot of the anthropogenic heat uptake and anthropogenic carbon uptake happens. It happens through a mixed layer process. And so the fact that our mixed layer depths are plus or minus a factor of 2 when the observed variability is really only about 10% is pretty crazy. So similarly, if we think about let's take different mixing models and see what they do to mixed layer depths, that's something we could think of. Let's take models, and this is a study that Ching Li, who was a former PhD student of mine, is now a professor in Hong Kong, at Hong Kong University of Science and Technology. We were interested in how much wave-driven mixing adds to the mixed layer depth. And so we did a bunch of things where we took a model and then added or subtracted the Stokes drift forcing to the mixing parameterization. And so these 2 figures show wintertime, January and July. January and July. And they're showing percentage of deepening of mixed layer depth when we add that Langmuir forcing. And each row here is a different parameterization of both the background part and then also the Langmuir adjustment. So this is one that Ching and I came up with. This is one that Ching and Brandon Reichel came up with. And this is one that Ramsey Harcourt came up with at the bottom. And so you can see that broadly, the amount of additional deepening you get percentage-wise due to the Langmuir forcing is kind of similar, kind of 10%-ish in summer and maybe 30%, 25, 10 to 20, 10 to 30% or something in winter. That's interesting. And now here's the wrinkle I want to throw at you. Which surface flux product did we use to estimate this? The right-hand side shows the Core 2 Large and Jaeger 2009 fluxes, and the left side shows the JRA 55 driving ocean fluxes, the Sugino et al. Fluxes. Yes, the change of mixed layer depth is still kind of ballpark in the same amount, but the differences in the mean mixed layer depth at a particular location between these fluxes and these fluxes are so big that you can't actually compare like the Langmuir version over here to the non-Langmuir version over here. The difference from fluxes exceeds the difference in adding Langmuir physics. So the climate models are really far out of whack, and the fluxes, now we're talking about episodic intermittent fluxes, in particular parts of it are poorly well known enough that it interferes with the process model assessment. So why do we care? Well, extending Galen's work out, you actually can use this through something called emergent constraints, where you constrain the observed properties of the mixed layer to make a prediction. And if we could improve the mixed layer, which we, based on that magnitude of change that I was just saying, which is about 5 times as big as Langmuir does, how much we need to fix the mixed layer to get it within the observed range, it would change the climate sensitivity of the Earth dramatically. This implies probably changes in the atmosphere and the ocean and clouds and mixing and all kinds and eddies and all kinds of things that are affecting those mixed layer depths. But if we could get it to the right value, you can estimate how much of a change in climate sensitivity is. And it's about a 20% reduction in the transient climate response, or a 45% reduction in the effective climate sensitivity range. And this is when you get to really big usefulness. An economist a few years ago estimated that if we had done this reduction, or twice as big as this reduction in time to make the changes for 2020, oh well, we missed that boat. But it would have been worth about $10 trillion in terms of the economic consequences to just have a more accurate estimate of how uncertain the future climate state would be in terms of the transient climate response, in order to change, to inform economic decisions about emissions. So now we're actually in business. We're close enough to something that has real consequences. So improving that mixed layer depth actually does link up to these pieces. So to close, how do we use the observed fluxes? So we probably can't use them to do global observations of those small residuals. We probably just let the ocean do that and then go measure the ocean heat content and get that out. Or let the ocean accumulate the long-term statistics of winds and observe the waves to get the consequences of that. But what we can do is we can go region by region and build regimes of how much those fluxes vary. So this is a nice regime diagram that we've had in a lot of different papers, which shows essentially the amount of winds versus the amount of waves along this axis. So on this corner, you're dominated by wave-driven mixing, and this you're dominated by wind-driven mixing. And on this axis, you're dominated by convective cooling, and here it's, wind or wave-driven cooling on this axis. And this white line is an estimate of where the upper ocean is across all seasons. So in this regime diagram, this is where we need to be to understand how strong, this is how strong convection gets sometimes. This is how strong Langmuir gets sometimes. This is how strong shear gets sometimes. And you can see these pink dots, we basically mowed the lawn over this probable region by running LES over all of those regimes. And we were sure that we were running LES in the right regime because we had these fluxes to rely on. Here's the stable condition. So this is when you're warming at the surface rather than cooling at the surface. A lot less has been done here. We probably need to do more LES in this regime. But as Peter Sullivan, who's on, will tell you, this is a lot harder to do LES of. Okay. So that's how we might use fluxes, is to get better at those regime diagrams. That's a time mean vision. There's temporal variation in the fluxes, which is really important and something we really don't understand. There's probably time history in those mixed layer depth biases that is an important thing that we really don't have a good grasp on right now from a parameterization or even a dynamics perspective. And for climate studies, it's going to be difficult to eliminate the small biases in any one flux type. So we're probably not going to be able to get down to add them all up and get really close to zero, regardless of what satellite technology we're using. So we need to get something like 1/10 of a watt per meter square imbalance overall to match all of the pieces together and handle the compensating errors. And they're big compensating errors because the errors in the wind affects the latent heat and the sensible heating as well as the wind itself. But what you can do is you can separate out those flux constituents and match those flux constituents against how they're modeled one at a time in the climate system. And that allows you to unravel the compensating errors that are in that very small net budget and go specifically after things like cloud physics will affect the shortwave fluxes, surface roughness affects the shortwave reflection, albedo reflects the shortwave reflection, long wave fluxes. There's absorption at different altitudes based on temperature, humidity, water vapor, atmospheric constituents. That's a good thing that you can track for the long wave. And then winds, of course, sea state, like we've already talked about, momentum exchange, latent heat, sensible heat, all of that is informed by knowing the winds and the wind stresses better. So we can example the large scale patterns to draw contrasts. Even though the net heat fluxes had a lot of stippled out regions where there was not a significant trend, it's possible that in these component by component analyses, you actually are getting significant trends. Some of them are much cleaner in terms of noise versus observed. So that's all I wanted to say. So to conclude, it's really complicated when you start thinking about what the CMIP flux biases are and means are versus observations. One trick you can do is you can use the oceans to keep track. Another trick you can do is you can go into this sort of process model conception and think about what you're really doing with flux observations as you're providing fuel for the process studies that inform particular parameterizations. And then if we did have better fluxes, we could do that for the mixed layer depth and process studies. And then by individually assessing the different flux components, we could, again, get at different processes, whether they be in the atmosphere or the ocean. That's it. So I hope we can discuss a bit. I'm going to jump out of full screen mode so I can see people and go
Thank
back
you.
small mode.
So questions for Baylor?
Yeah. There we go.
Looks like Eric, there are a bunch of hands up. It looks like Eric Desaro is waving his hand.
Okay.
And
Yeah, I
Peter
couldn't
Sullivan
figure
has
out
a hand.
where the hand button was, but okay.
We'll let Eric go first.
Hey, Baylor, that was fun. Could you go back to the slide on the paper with Hall and explain it again?
The paper with Hall, yeah. Okay.
They had some scatter plots that apparently are important.
Yeah, the scatter plots are important. So let me go back to this scatter. The first thing you want to read off this scatter plot is this vertical bar is the observed range, mixed layer depth in those regions. That's what the possible range should be. But instead, the CMIP models have this bigger range. So they are from about one in this northern ocean. Some of them are 1/10 the depth they should be, and some of them are about double the depth they should be. The big cluster is kind of close, but if this is a plus or minus 2 sigma, we're talking about 3, 4, 5, 6 sigma kind of deviation in what the observed mixed layer depths are. So it is not a statistical anomaly. There is broken physics in the mixed layer depth in a big time in all 3 of these important regions. So that's the light take. Now, the vertical axis, what we're showing is we actually emulate the climate models to predict, to get to this future projection piece. And so the way that you use that mixed layer depth is you get the parameters of your emulator and you correlate them against the mixed layer depths across the model ensemble, and then you squeeze the allowed mixed layer depths, changing all the parameters as these models slide into the observed range, and then you ask what that set of CMIP models would be. So the thought experiment is, what if I could fix the mixed layer depth? What consequences would that have for things like the climate sensitivity? And that's what this figure shows. So this $10 trillion result is, if I could fix all the problems with mixed layers, which probably means fixing a lot of other stuff because it's not caused by mixed layers, it's just correlated to mixed layer problems, you would change the uncertainty across the climate models in terms of the amount of warming by big percentages. Does that make sense?
So just to say that in a different way, if you wanted to constrain climate models, it's as important to get the mixed layer climatology right as it is to get the flux climatology right.
Yes, sure. And those two are related. I mean, that's the...
Of course, but
Yeah.
one appears to be an easier problem than the other, perhaps.
Maybe.
I didn't say which one.
I don't know. They both seem very hard. I think the errors are quite big, and the noise is quite big, and the flux and the mixed layer depth problem. So we have a lot of problems here. There's a lot of room to improve.
Okay, let's go to Peter Sullivan.
Hi, Baylor. That's neat. Could you just comment how sub-mesoscale stuff in the ocean changes all this?
Sure. So I was estimating these mixed layer depth changes for Langmuir. That's essentially the same order of magnitude in change in the mixed layer depth that sub-mesoscale is. They tend to be in opposite directions, and they're similar. They are linked to different fluxes, so they're not changing in the same way, but they are changing of about the same order of magnitude. And so you get the same improvement of mixed layer depth from adding Langmuir as adding sub-mesoscale in terms of the reduction in RMS bias. And so what we need to do, though, to get these mixed layers of all of the models in the CMIP ensemble, most of which do not have Langmuir, many of which do not have sub-mesoscale, like that would help some to narrow this, but to get them all in the pile to be in this observed range is more than the Langmuir, adding Langmuir and adding sub-mesoscale by about at least another factor of 2.5, probably a little more than that even. So that's the comparison point. So now you're like, well, what else is there? Well, there's vertical resolution. There are obvious things like that we probably should be doing better on. There's also cloud physics, air-sea flux parameterizations. All those pieces have to be improved, similarly to what the order of improvement we've gotten from Langmuir and sub-mesoscale. We need to keep working on those process level representations in the climate models to keep pushing those parts better together. Obviously, the whole point of this is having better flux observations would really help, because we could do forced models and forced process models in particular, and make sure that we were really doing something realistic and compare back to observations there and see if we're getting closer in that process model step and then with good process models, conceivably we get better climate models through what we learn from the process models. Does that make sense, Peter?
Oh, sorry.
Hi, Baylor.
Hi.
Thanks for the talk, really nice. And I really like the way you open up your talk with a tough question, which is about energy budget imbalance. And that is at heart of the surface flux products, which and there's so many types of uncertainties. And no single products can balance the budget right now. And but also I love the way you circle around and about whether how to use the ocean variables like mixed layer and the waves to diagnose the flux. But essentially, the question is what's wrong with the flux products? And that is the key questions in develop our second version of OE Flux products, which you use the early version is sent you for the IPCC report. That's our first draft. And we have the products calculated for a couple of years, but I cannot, but I still hold it for releasing because one key question is the products right now is about a 13% upward increase from the first version. So you will ask what we did, whether this like a 13% jump is reasonable. And that is the main issue for the last couple of years. So I've been checking and validating and not with similar products, but with echoes, because that is a dynamic balanced version. And seems like the key issues people seldom talk about is parameterization. Actually, the central issue is about drag coefficients. So if you change a little bit drag coefficients, and especially the drag coefficients right now in the treatment regime currently has an error, because the most drag coefficients is validated in the tropical region, and in the treatment regime, I believe probably because of the swell effects on the drag, not really parameterized. So, and if you kind of increase drag coefficients in that regime, and the whole pattern changed. And that 13% increase in the fluxes and actually is very consistent with recent budget analysis from the Stevens and from the Ruddell to study, because it's balanced not only a water flux, it's balanced near to zero with the E minus P minus R river runoff, and the balance with series radiation to single digit around 6 watts per meter square. Probably still one order bigger than the 0.7 watts per meter square, but it's a step forward change. So if you're interested, I'll be happy to give a review about what we are doing in terms of balance in that regard. But on the other hand, it's just like a mesoscale variability. So you change the mean background, you change the mesoscale variability. And you have two versions about a call 2, and also it's like a GI 55. So can you see, and is a difference is due to this mesoscale variability difference in the model or due to the mean?
So both of those are essentially they start from a reanalysis product. So they have a lot of atmospheric variability with observed mesoscale underneath them, at least when there is satellite mesoscale available. So the SSTs do have the mesoscale in them in both. But my understanding is that even the data analysis, the data assimilation mathematics can be as big of a signal among the different reanalysis products as the forcing variables is. So it's not only the forcing, whether it has the mesoscale in it or not, they both do in theory, at least in recent years, but they don't have, those comparisons I was showing were for recent years, but they have biases in the forward model that they're using. So the forward weather model piece is different and differently biased. And then they also have somewhat different data assimilation algorithms, which both of those lead to residuals. So it's a understanding what's in the reanalysis product is very hard, because all of those different pieces play some role. It's hard to pull them all apart. And so I don't know why they're different. I just know that we get higher resolution atmospheric forward models that help some, We get better parameterizations that are going in the forward models. That helps some. We get better at data assimilation. We get bigger computers that can do more expensive but more accurate data assimilation, like Ensemble Kalman instead of other things. All of those steps are steps along that process to try and reduce them, reduce the distinctions between those. But it's not, I wouldn't say it's cleanly just a physical forcing difference between them. They, in theory, are being forced with the same piece. Now, they don't have coupled mesoscale variability at all in either of those products. They're atmosphere only models. So the ocean doesn't respond to winds and things like that. That's sort of another level of complicated refinement. So coupled forecast systems also seem to do some things better. Certain places in the world, coupled modes are really important to have, but I wouldn't say that's the leading problem either. There's kind of a mass of problems in making reanalysis more accurate.
Right. So that's questions about the atmospheric models because they never balance at surface, they balance at top of the atmosphere. So
yeah.
And it's not good starting point if you want to know how the energy balance is surface. And for the ocean models, I mean, and just wondering, what is most important? Is the mean, total mean, or is the resolution? I believe the GI55 is about 0.6 degree. I cannot remember exactly, because that data is extremely unbalanced on surface. Evaporation or letting flux is blow up too much. So, and I have not really paid much attention to that product, but it's just like for increased resolution. And just wondering, just like how the spatial resolution importance, I mean, must be important. I know from some mesoscale, but even with the same kind of balance and some, I mean, the products balance a different way, and whether how the mesoscale variability or representations by the flux products affect mixed layer simulation. I don't know. I was kind of, it's complicated because your mixed layer is not only the wind, but also the buoyancy flux altogether.
So there are a couple of modeling results that kind of get at that to some degree. So I mentioned Steve Griffiths has been leading a lot of nice papers, and then there's a new version of the GFDL coupled model where they don't see significant drift in ocean heat uptake from initialization, which means that the ocean model isn't trying to grab more deep ocean heat content than it should. If you initialize from observations, it stays put. And so that coupled feedback that I was talking about, if the ocean starts gobbling up heat, then it'll just lead to an imbalance at the surface, because really it's, kind of, if the deep ocean wants more heat because it's trending in the deep ocean somehow, it will do whatever it needs to do to the fluxes at the surface and the temperature at the surface to make that happen. So
it's probably depending on time scale talking about.
Oh yeah, this is over long time scales, over climate time scales. So that process is part of what's going on, and that gets better the higher resolution the ocean model is. So the mesoscale parameterizations are definitely a problem there. The GFDL, they find that I think it's an 8-kilometer model. Global is the first time they're able to get really minimal drift when initialized from observations. So they're saying that 8-kilometer mesoscale resolving in the ocean is really important for getting those vertical heat transports right. That's on top of mixed layer mixing biases, but just in the mesoscale transport part. So on that decadal trend piece. When you think about the submesoscale and the upper ocean, then there's all of the stuff about the eddy killing effect that Dudley Chelton and Lionel what's his name? Renaud have been talking about. That's really important coupled physics that says that you can go quite far away from the truth in terms of the submesoscale eddy energy or submesoscale frontal strength by not having the right feedbacks connected to the atmosphere, not having that be on sufficient resolution, submesoscale permitting resolution. I think that probably when you get into the sub-mesoscales, the time scales are so fast, they're so close to the flushing time scales of the mixed layer and the heat exchange with the atmosphere that there's no longer this enormous heat capacity imbalance. And so you can't just think of the ocean as being the reservoir and the atmosphere as being the driver, the way that you can on the larger scale. And so you probably do have to go into coupled systems to really understand the sub-mesoscale fully.
Yeah.
That seems to be where things are going from a model perspective.
Right, and absolutely agree with that. So, but my last question is, what's your recommendations for surface flux products?
Current flux products. I don't know. I'm not a flux person. I'm just excited to learn.
From the user point of view, just
And I
from
also
the
hope
user
that,
point of
I will
view,
say,
what you need.
from the perspective of the Oasis goals, I mean, all of these products would get better if we had better observations of the fluxes and of the surface conditions at higher and higher resolution. That will make the reanalysis versions better. That'll make the direct products better. That'll make all of those pieces improve. And also we get better observations of the processes underlying as well. So I was talking with Sarah before we started about saying, oh, normally I would say we just need to have the Stokes drift and the currents together, and then we can figure out how that all works. But, like this is a slightly different take that I was doing here. So I don't have a favorite flux product. I will happily, the IPCC approach to having multiple products is you just put them all on the same graph. And then you say, all of these, we don't know which of these is best. Our degree of ignorance is measured by the spread among these different products. So I kind of like that approach, but certainly some of them are probably outliers in one way or the other when you do that. But that's how we move. That's how we learn and get better.
Thank you.
Yeah.
Additional questions? And maybe I'll just say, I really appreciate the message you put forward, Baylor, to that if you want to know the net flux, it's sufficient to just put out Argo and measure the ocean.
Yeah.
But if we want to know the processes, we do need additional measurements. I did wonder, though, you show in the comparison in the work with your student, Galen Hall, you show this very narrow range of mixed layers. And I think the observations of mixed layer show a lot more variability over the course of a year or over multiple adjacent grid points. And so you're looking at some sort of average product. Is there information to be gained from the measured spatial and temporal variability?
Probably. We had some of those are annual means and some of those are like seasonal means. So that's what's really hammering down that variability a lot. And they're obviously very large spatial means. They're cutting over all longitudes at a particular latitude range. So they're very wide averages. So that makes that range quite small because of the central limit theorem essentially is why it's getting small, not because the underlying variability is not bigger. Probably there's a lot more to be learned from the underlying variability. We might even be able to take a bigger chunk out of that future climate change uncertainty spectrum if we got the variability right. So convection not only of the right magnitude, but in the right places and those sort of things for sure. And
I think that's one of the goals in trying to expand an observing system to capture those anomalous or extreme events that might be driving the system.
But it's a little, one thing that's very complicated with trying to assess coupled climate models is that the mismatch with observations may not actually indicate the causal part of the problem. So you might have a model that has a perfect AMOC, but it has terrible locations of deep convection. That happens a lot, actually. So there are lots of papers talking about how can we possibly do this if all deep convection is in the wrong place. Some of those models have really good overturning in terms of what they're observed. So intellectually, we think that if it's all in the wrong place, how could it possibly get the right answer? But a lot of these emergent phenomena have other constraints on them that are not so geographically specific. And I think so there's room for theoretical improvement there too, which is just to understand what those parts are and really focus on the parts of the geographic or seasonal differences that matter. And I don't really, yeah, I mean, it probably does matter, but I can't even think of a way to estimate how much it matters from the present system. This first pass that Galen and I took was trying to just get a ballpark as to how much of the climate change is correlated with mixed layer depth. That was what we set out to do. So that's the first pass.
Nice. So any further questions? If not, we are just about at the end of the hour. And so people can, of course, email Baylor with lots of further discussion. And I'm sure there is lots of further discussion. And we'll thank you very much for doing this.
Yeah, thanks
Thanks everyone for participating.
Thanks everyone for coming. Thanks for the questions.